I will have your big labs, your full lab write-ups, I think I told you this maybe last time, that you turned into me 3 years ago or something like that. I will have those back for you on the next day I see you, which would be what, next, I guess, the Monday after, whatever. So you'll get those back, but you'll have 2 labs that you're doing next week. One of those you will need to write up as a full write-up, okay, by Friday the 19th. Does that make sense? The day before, or the last day before break, okay? So you'll do a full write-up for one, and you'll do a data analysis for the other. So you need to do data analysis for both, but you'll do a full write-up for one of them. So the labs are not big, scary, messy labs so much, but they are ones that you should take careful data for, that you should think clearly through, okay? And the work that we're going to do today, I think, will help you to be successful at that, okay? So what I'd like you to do right now is to pull out your notes and also that yellow sheet that we did last time. Did I give you one of these already? Okay. Does anybody need one of these? I do want you to have this out to take a look at because we're going to look at this pretty carefully today. You will also need to have your have a calculator out because we're going to try and figure out what these numbers in here really mean. I know that the last time we were together, we started looking at this, but I don't think we got very far. Am I remembering that correctly? Yeah, Emily's giving me a big big head nod there. Okay, so let me just kind of remind you what we did so that you're back in the game with me. We watched this video of the spring bouncing up and down, and I made those dots. And that made these really nice sine curves that you have on your yellow sheet and I've got up here. Okay? So we agreed that they were sine curves. We agreed that that kind of makes sense based on the chart that we filled in on the front. Correct? Yes? Is that, yeah? Yeah, that kind of makes sense. And then we have to figure out what all of the numbers that are in here mean. Okay? So at the end of class last time, we were looking at this big, scary form of sine. That's what exists on your yellow sheet. Yes? Okay? That's what exists here. That A sine BT.
From Miss Cross.
Oh, I knew they were somewhere. Thanks. A sine BT plus C plus D. I think I probably sent this to you before, but I just want to reiterate. The C and D here are really just shifting the graph. So we don't really care about them. It basically will be adjusted based on when I hit go, when I started taking data. So the C and D, I don't want you to worry about. The A and B are things that I do care about. I think probably we said that that shift will give us a sine or cosine. But just to be really clear about why I'm going to choose cosine, if you look on the other side, the chart side of this, it makes sense that an oscillation of a mass on a spring is going to start at either 1 or -1, doesn't it? It's not like you're going to have a mass hanging on a spring and just spontaneously it's going to start from equilibrium and start bouncing. Like, that doesn't make any sense. So we're going to call it a cosine. Okay? But again, sine and cosine are really one and the same thing. It just depends on where you start your time. Sine and cosine both have a minimum and maximum. What's the biggest that cosine can be?
1.
And what's the smallest it can be? -1. Kind of like these oscillation things that are happening here, right? So if cosine is 1, then the displacement is going to be at its maximum. And again, if we look at the yellow sheet, the displacement at its maximum is the what? Take a look at the yellow sheet. You have it written on there. I know you do because I saw it. The maximum displacement. So you look at the displacement column, look all the way down to that bottom row. It's the amplitude, right? You guys with me there? The amplitude is the maximum displacement. So if cosine of whatever it is goes to 1, then this thing here dictates what the displacement is. So that letter A up here actually, you can say means amplitude. Okay? So if you want to write something down with that, maybe a note that cosine goes from -1 to 1. So the biggest that that displacement can be is when cosine is 1. That is your amplitude. If you take a look on the graph on the yellow paper, looking at the top one, that's the displacement graph. What is the value listed for A? What do you see there? Take a look. What does that A value say? Do you see what I'm talking about? What does it say, David?
0.0365.
0.03. Is that right?
365.
What does that mean in terms of a mass bouncing on a spring? If A is the amplitude, what are the units for that, do you think? Meters. So that's 0.036 meters. How many centimeters is that? 3.6 centimeters. And if you look carefully at the video, let's just kind of take a glance over here. We can look at this, and if you watch this thing oscillate up and down, I kind of wish now that I had done this better that I used, this is like the decimeter side. If I had used the centimeter side, we could see the oscillation is about 3.5 centimeters. So it actually means something, okay? It means something. Now, this gets into the meat of things a little bit more. I told you, I kind of snuck it in there, that this coefficient here is not called B, something that doesn't mean anything to me, but it's omega, which is something that means nothing to you yet, right? We know that it exists up there, that it's the last Greek letter. Okay, we must be almost done, or I don't know, not really. Okay, but omega is related to frequency, and like I told you before, we'll get to know that really well second semester. But for right now, let's just say, okay, I'll trust you, Miss Carveling. Sure, that sounds okay. I want to show you what this means. Omega is related to frequency. Frequency is also related to another thing that we defined a couple days ago.
Period.
The period. How can I find the period of this oscillation based on this graph? Any idea? How could I do it?
It's from where you start and then you go back.
So it's a full...
I want to say a full period, but
but that's redundant.
Yeah.
There's a word for it. What is it? It starts with a C. Full, or you could say full oscillation with a silent C at the front, right? Yeah, or full cycle, either way. So I'm going to look from crest to crest because I can. Does that sound okay? And if I look from crest to crest, I'm going to remind you that there's a really nice tool up here that says stat. You might want to write that down so you don't forget. Stat, that little button, and that tells you the statistics for the set of data that you're looking at. So right now I have this statistics thing set to look from here to here, so the maximum is going to live in there. And I'm going to tell you right now, so you need to write this time down, that the maximum for this oscillate, or that crest, happened at the time 1.204. 1.204. That number means very little to you in and of itself, but I'm going to take a note at what time it hit the maximum over here, okay? And I don't actually have to move this second side because this one is much higher. So I'll tell you that the first crest happened at 0.3370. We'll say that again, 0.3370. So given those two pieces of information, I would like for you to determine the value of omega given this statement. I'm going to let you work with your partners and figure out the value of omega given this statement. Okay, you have enough information. Got to put it together a little bit. Good Friday. Okay, so it sounds like most of you are there or almost there. So I want to get caught up with you. Given those times, Are you able to find a period?
Yes.
Yeah, what did you get? Isabel, what did you guys get for the period? Or did you write down a number for that? Like for the period of oscillation, like big T? Did you do that?
Probably, but I don't think.
You didn't write it down.
I don't know. Well,
Tell me what you know. How about that? Let's back up.
okay. Well, we figured out the frequency.
Okay. Little f?
Yeah.
That sounds okay. What did you get for that?
So we take the difference between the 1.204 and then the other one, and then because it's over one cycle, is that the period?
Yes.
Then it's divided by 1.
Yes.
So
1 divided by, yeah. So what did you get for the frequency?
1 divided by.
So frequency is 1 over period. Does that make sense? So let me back up because we didn't say this explicitly before, but I want to make sure this makes sense. Can I see everybody's lovely eyes up here for just a second, just so that I know that you're at least maybe hearing me? So the two numbers that we got, those 2 times, we need to subtract those to find how long it takes, right? Does that make sense? So that's going to be your t. Do 1 divided by that, because time is in seconds. Frequency is in cycles per second. So you're going to take that t and do 1 divided by that to get your frequency. And then, so let's make sure we're okay with numbers. What did we get for that frequency, for that value? Did anybody write that down? 1 point what?
156.
And the units for frequency is what? Hertz. Okay. And then from that, we can find omega because we're just going to do 2 pi times that number. And what did you get for that then? 7.2524, something like that? Okay. Now, what I'd like you to do, first of all, is to keep in mind that this is all experimental data, right? So it's not perfect. But I want you to look carefully. I claimed that this thing is omega. Take a look at the B values, or the B value for displacement. Take a look at what it was. What was it? That's pretty close, right? I mean, plus or minus a little bit of error, but yeah, that's pretty darn close. So that is what omega is. So I guess if you really wanted to, you could write, instead of omega, you could write 2 pi f in there. It's just that we don't usually see it that way, so I don't want you to get too, stuck in that way. Does that make sense? Okay. So far, so good? Okay. Now, I want to look down at the second graph. The second graph is a graph of velocity. You'll notice a couple things about that graph. One is that it's also kind of a sine curve, but it's opposite, right? This one has a maximum here when that one's at 0, and this one has a maximum up there when this one's at 0. So it's shifted by a little bit. Okay? Is that okay with everybody? If we start this one, if we want to do this, if we want to take this really, really carefully here, we can say that this one starts, cosine would start right there. This one starts at 0. Do you agree? And for my friends that enjoy graphing sine and cosine, this is going down here, so this is actually going to be a what? Is it going to be a sine? Does sine go down first?
Negative.
It's going to be a what?
Negative sign.
It's going to be negative sine. Okay? So that's just a hint at it. If we're going to write down a velocity equation, there's going to be a negative sign involved. There's a t, and what value do you see when you look at the thing that is that b value here in the velocity graph? Take a look at the velocity graph. That's the bottom one. The coefficient inside, the one that's right next to the t. What is it?
7.30, so omega.
So it's omega again. Yeah, it's omega again. This next step, for my calculus friends, is going to seem really obvious and say, I love chain rule, right? I heart chain rule. For those of you that don't know calculus, I don't want you to freak out. It doesn't matter. It really doesn't matter. I just want you to take a look at that number here and do a little experiment for me. I want you to take the value of A and multiply it by the value of omega. Go ahead and do that. multiply A by omega and see what number you get. And then take a look at the value that's in front on the velocity equation. What did you get? Did you get something interesting? What'd you get, Isabel? You got the A thing, right? Yeah, yeah. So this thing here, instead of just being amplitude, actually is going to be A omega. Okay? So, again, for my calculus friends, you're like, oh yeah, I got that. But if you're not that person, that is so okay. You're not missing much. It's all good, okay? Just know that that's where that's what it is. That's okay. All right? Life is good so far? Okay. Now, let's see. Let's think about this carefully. I'm trying to figure out how carefully I want to think about this. Not too carefully yet. I want to do one more. I didn't actually graph the acceleration, but I want to tell you what it is. I'm going to give my calculus friends a chance to show off their mad derivative taking skills to make a prediction for me. What do you think this is going to be? Anybody?
Negative cosine A omega. No. Go back.
I agree that it's going to be a negative cosine.
Quick chain rolling.
This. You can do this. You can do this, calculus people. Yes, and again, I don't want you to feel bad if you can't. Hold on just a second. I just want to make sure everybody gets a chance to play. Did you get something, Allison? Are you a calculus person?
Yes.
Okay. What'd you say? What? It's like the coolest thing ever. Oh my gosh.
It's easy once you remember how to
I
do
heart
it.
chain likes your new shirt.
Chain rules the best. Chain rule, all the chain rules.
There are actually things I'd like more than that, but that is pretty funny. What's up? What did you get? Yeah! Oh my gosh! That's what it's going to look like, A omega squared. You say, okay, that's fine. Now again, if that's not your cup of tea, that's okay. You're not, like I said, it's not a big deal. I just, let's give them a chance to show off for a second. Life is okay? You say, okay, sounds good. Hold on to that thought for a minute. Leave maybe 3 or 4 lines there, and I want to write something else down that we all can do. We all have got this because we all know how to draw free body diagrams, right? Yeah, we do. Here it comes. Woo! Mass on a spring. There's x equals 0. Talk to me. Is there a net force acting on that thing?
Yes, there is.
Yes, there is. Is it accelerating in the y direction, assuming this is actually sitting on the ground and it's frictionless?
No.
No acceleration in the y direction. Is it accelerating in the x direction?
Yes.
It will be, right? So F net, I'm so excited. You guys are going to be so excited about this. This just brings it all. Oh, it's so good. Okay, here we go. So F net equals negative kx. Would you agree with that statement? Because the only force acting is the spring force that's pulling it back in that direction. Okay? We also know, because Newton said so, that F net has to equal what? Mass times acceleration, ma. And this, my friends, is a pretty straightforward statement, don't you think? But it is Friday Fun Day, and I like to make things more complicated. Are you ready? Are you ready? It's going to be great. Here it comes. But I will promise you that the end of the result of this will be fabulous. So you got to hold on to your hat. Here we go. Okay, so take a look. Oh, did you have a question first?
Doesn't the 2 come out in time when you take the derivative of that? Unless I forgot.
Hold on. Are we taking the derivative of this?
For acceleration to get velocity?
You have to integrate to get velocity. Derivative to get acceleration. Is that okay?
The 2 just magically disappears because you can do that in that.
No. So okay. So all you're doing when you take the derivative of this, it's with respect to time.
Yeah.
So this is all constant. So the only thing you need to take the derivative of is this. So it's going to be negative cosine, or excuse me, just going to be cosine if you take that part, and then you take the derivative of the inside. The derivative of omega t is just omega. And the reason that that happens is, so that's why it's squared, because there was already one sitting out there.
Okay.
Is that okay?
Yeah, maybe if I stare at it, I'll understand.
We can talk about it later too.
Okay.
I'm very happy to do that. Okay, so you ready to make this ugly? It's gonna be fun. It's gonna be fun. All right, you know how I had an x in that equation? Yeah, that cute little x right there? Instead of writing x, we're gonna make it this big nasty thing. A cosine omega t. There's also an a in that equation. I'm gonna put this whole big monster in there. Are you so excited, Chris? He's like, what are you doing? You're ruining my whole Friday. No, it's gonna make it good. Just hold on a second, I promise. Pain happens first, then beauty. Here we go. Here we go. Negative k times a cosine omega t. Is everybody okay with what just happened there?
Yeah.
I think.
All right.
How would you plug in for acceleration?
No, I plugged in for displacement. That's the displacement one.
Okay, yeah.
This is my displacement right here. And then I'm going to write m, and now I'm going to plug in for acceleration. This is the bigger, scarier, nastier one. Negative a omega squared cosine omega t. Well, that's pretty. Yay. Ugly. Right? I get it.
Well, you got rid of a negative sign on both sides.
Whatever. It looks really disgusting. I will be completely honest. The first time I saw this, I was like, oh my gosh, this scares me so. Like, there's cosines everywhere. But that's great that there are cosines everywhere because there's a cosine omega t on one side, a cosine omega t on the other side. So what happens to the cosine omega t? They're gone. Well, that makes life so much better. Is there anything else that we can cancel out?
You can cancel out a negative a from both sides.
Yeah, I can get rid of a negative sign, and I can get rid of an a, and then, friends, it looks a whole lot less scary. So we've got k equals m omega squared. How are we doing? Is that okay? Okay, so a little math magic just makes this so much prettier. True? Solve that for omega. And this is when the cool stuff happens. I'm so excited for you because it's all going to come, like, oh, it's going to be so cool. All right. Are you ready?
I'm ready.
Okay. River is so excited. Now, I'm going to write that up here again just so I don't forget. So omega is equal to the square root of k over m. I'm going to write it down again. Omega is equal to the square root of k over m. Remember when we were talking about this one before we started writing all this craziness down? I said that this thing out here is going to be the maximum, right? That's the maximum value for the displacement. The maximum value for the velocity is going to be what, according to this equation? A what? A omega, right? Does that make sense? But omega is the square root of k over m. So I'm just going to write this down here. V max is a times the square root of k over m. Is that okay with everybody? Turn your yellow sheet over. Look at the second column, last row. Maximum velocity is what? How cool is that, right? I think that's pretty awesome, myself, if I do say so. Okay?
Yay, Grandma.
Everybody see that? Yeah? Did everybody have like an ooh-ah moment? Like you should be proud of yourself because you figured that out without this craziness. But it all fits. It all fits. Let's do one more. What's the maximum value going to be for the acceleration? Take a look up here. What's the maximum value going to be for the acceleration one? Say it. A times omega squared. Yeah. The acceleration max is going to be a times omega squared. Well, omega is the square root of k over m, so that's going to be a times k over m. Take a look at your sheet again. Oops, you can't see that. There you go. What do you have for the maximum acceleration? Huh? Are you guys not as excited about that as I am? I thought that was so cool when I first figured that. I was like, whoa! It all works. I think it's cool. Maybe you guys are like, whatever. We knew that already. Psh. Carbling, you're just a little slow. I don't know. That's pretty cool in my book. Whatever. Let's see if I can impress you some more. Questions about that before I move on? Okay. One more little piece. We don't really know what omega is, do we? Like, we haven't really been playing with omega. I just told you that I could have called it Joe. That thing is Joe. You don't know. You don't have any clue. All that I told you, though, was that Joe or omega or Larry or whatever you want to call it is equal to 2 pi f, right? Instead of omega, I'm going to put those together. I'm going to write 2 pi f is equal to the square root of k over m. And I'm going to solve that for f. So f is equal to 1 over 2 pi times the square root of k over m. And this is not something that you're probably like, whoa, that's so amazing. Because my guess is that maybe only 1 in 10 of you stayed up nights since accelerated physics wondering where that equation came from. But this is the equation that we talked about and that we worked with in accelerated physics. And I said, you just have to trust me that it's right. Take AP physics and someday I'll show you how. And that day is today.
And they have these on ACT questions.
Yeah, they do all the time, right?
Yeah, they talk about the past.
Yeah, yeah.
Too many tests.
She's like, that's why I'm staying up at night, because I can't. Yes. But this is where it comes from.
No, they give you the equation.
But they just want to see if you know how to manipulate it.
Probably math.
Yeah, yeah. But I mean, it's
Because the science is just like really even.
Yeah,
Yeah,
you don't have any graphs.
it's a good problem because it has square roots and it has fractions and it has stuff. Yeah.
Yeah, I know. You just look at the equation.
It's not hard, right? I mean, like, psh. Okay. Questions about all of that before we move on? Question? Are you sure? Okay. I couldn't tell. Okay. I've got a ranking task for you to look at. Because you missed them, because we haven't done them for a few days. I know it's been a hard time for you. Let me tell you about this one. A block rests on a frictionless surface. It's attached to a spring. It's attached to a spring. The other end of the spring is attached to a wall. 4 block spring systems are considered. The springs are stretched to the right and distances are shown in the figures and then released from rest. The blocks oscillate back and forth. The mass and the force constant of the spring, so that's the K value of the spring, are given. It says to rank the frequency of the oscillatory motion of the block. I'm going to let you take a look at that. I want you to do it by yourself for a minute, then I'll give you a minute to talk. Station, shall we? Go, Seth!
I got A, B, B, C. A is greater than B.
A is greater than B
B.
is greater than C?
Yep.
What do you guys think?
I agree.
Do you agree?
Yeah.
Can somebody explain it to me? Not just yes, but why? V, what did you guys do? Can I ask you? Is that okay?
I saw that 1 over 2 pi. You're just multiplying. I used the frequency equation we just got.
Okay.
And
So frequency is 1 over 2 pi.
times square root of k over m.
Okay.
Yeah, and 1 over 2 pi is a constant that you're just multiplying, so you don't really need to. And then same with the square root because you're doing it to every single one of them.
Yeah, that's awesome.
So I just took the force of the spring and divided it by the mass of the block.
Cool.
So,
So like 5 over 1
yeah.
and 5 over 2 and 4 over 5 and 1 over 1.
Yep.
Is that what everybody else did? It's a pretty straightforward question, right? No problem. Sweet. Okay. So some things are masses on springs and they really look like it, and some things don't. Don't scream. It's a spider web. Oh no, but it's not that scary. You can handle it. It's not that bad. I'm going to make it bigger so you can see it. Now it's a really big spider web.
0.3 kilograms. That's a big swing.
No. A spider of mass 0.3 grams.
Gotta get
Ah!
out of here.
Yeah, right? Waits in his web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. What is the spring constant for the web? That's the first question. And then the second question says, at what frequency would you expect the web to vibrate if an insect of 0.1 grams is trapped in addition to the spider? Go. Bad. All right. So the algebra is a little bit tricky, but I think you should be okay with it. We sometimes need to practice our algebra a little bit. But what are we getting for A? What did you get for the spring constant? 2.66, 2.7, something like that?
Yeah.
Units are what?
Newton meters.
It's something. What is it? We can remind ourselves if we need to. If we need to figure this out. There are often times when students walk up to me during a test over this and they're like, what are the units of K? And I'm like, I don't know. Figure it out. So I'm going to tell you right now, this is how you figure it out. You know this is true, right? Hooke's law, an easy thing to remember, and it's on your equation sheet. You have that. It's like your security blanket all the time. What are the units of F? What are the units of X? Meters. So we can work from that to figure out what this is, right? So you've got newtons here, you've got something here, and you've got meters here. How are you going to get rid of the newtons and the meters? I want all of my units to work out, so I need a newton on top, right? And I need a meter where? Is it newton times meter? What are the units, guys? Do you understand what I'm doing?
Yeah.
Newton over meter. Do you see what I'm doing here?
Yeah.
Because then these meters will cancel with these meters, and then you've got newtons on both sides. So what are the units of this thing? 2.7 what? Newton meters?
No.
Newtons per meter. Okay? I know some people said it before. I get that. But I'm not convinced that everybody understood it. That's why. In part B, you're going to use the same spring constant, right? Because it's the same spider web. Same spider web, same spring constant. So for B, you're going to use that spring constant. You're going to use the mass and find the frequency. What did you get?
13 hertz.
Do we all agree with that? Is that okay? Okay. Issues, questions, concerns here? Okay. So we have a mass on a spring. It follows Hooke's law. We have the spider web. It follows Hooke's law. How many of you saw the movie Tangled? Did any of you see Tangled? Yeah, like this. It came out a while ago, right? About the girl with the long hair, I guess. I think I tried to watch it once. Was not very successful. Not because it's bad. I just think I probably got distracted. Did you know? This is a trivia question that probably will never help you in the world, but I just wanted to share. They employed a physicist on the animation staff for Tangled.
I can see why, though.
Because her hair acted like a spring, and so when they were trying to predict what would happen as her hair was flowing, they used Hooke's law to make those predictions. It's pretty cool. I thought it was neat. I heard an interview with the physicist that worked on. I was like, wow, that's cool. That's a good job for a physicist right there. I don't know if that's a lucrative opportunity to always work on those, but I thought that was pretty cool. All right, questions about that? I just thought I'd put that out there because it's kind of fun. Okay. I don't know if you've ever noticed this, but I like to do things out of order from what I tell you, right? Have you noticed that? Because we've got a little time, I want to do this. I'm going to jump around a little bit. We're going to look at what is in your book 16.7 and 16.8. And the reason I'm going to do this today is because it seems to fit well, and then we'll talk about the pendulum more after you've done the lab. So I'm just kind of counteracting what's going to happen later so that I know we have time later to do this. So 16.7 and 16.8 are the real world of simple harmonic motion. When we were looking at our yellow paper, and we were looking at the full cycle that happened here, the amount of energy that we had in A, how did it compare to the amount of energy in B? It was the same, right? Does that make sense? Which was the same as in C and in D and in E, which implied that the energy always stayed constant. Yes? Conservation of energy, sure. If the energy stays constant, what does that mean about the amplitude?
The amplitude will stay constant as well.
The amplitude is going to stay constant forever. Does that really happen?
No.
No, of course not. Why not?
Friction, air resistance.
What? Why not? Why not?
Friction, air resistance.
Heat, all kinds of stuff, right? Okay? There's all kinds of stuff. There's a lot of losses. If we drew an energy diagram of this, let's do, shall we? Yes, please. Join me. Bless you. Oh my goodness. If this is A, if this is picture A, woo! The first picture in this chart. I also want you to draw B. And just for kicks, will you also draw C? So A, B, and C, that's these three right here, A, B, C. Will you draw an energy bar charts for those three pictures on your notes? Feel free to talk to each other. That is just fine. A is the first one, B is the second one, and C would be the third one. This is not intended to be a tricky question. It's just leading us into a nice conversation. Okay? All right. Okay, help me out with A. I don't know who's going to do that. Chris! What'd you guys have?
All potential.
All potential. What kind of potential?
Spring.
Spring potential. What other kinds of energy did you have available at your disposal? Kinetic. And how many bars did you have of potential energy, spring potential energy?
3.
3, okay. You are in control. You get to drive that train. All right. Everybody okay with this? Maybe you had 7, maybe you had 100, I don't know. However many you wanted, but you had to do something like this. Emily, what did you guys say for B?
We said that the spring potential energy has 0.
Okay.
And then the kinetic energy would have 3.
What do you guys think? Does that match? All right. And then Will, what did you guys have for C?
I had 3 bars of potential energy and no kinetic.
And how much kinetic?
0.
0. Something like that. That's pretty straightforward, right? This should not be a surprise. Now, this is for an ideal system. In a non-ideal system, you said that the amplitude is going to change, right? So how is that going to affect these bar charts?
It'll become less.
What, David?
Less energy. The energy goes the other way.
Okay, yeah, but tell me more. Like,
Alright,
so
well-
is this one going to change?
Probably not now.
No, because that's our baseline, right? So
Yeah.
whatever. What's going to happen at B?
Well, it's going to change the kinetic, but there might be less kinetic energy than there was with potential energy.
Okay, so like maybe instead of having 3 boxes, we have 2 and 7/8, or maybe let's just make it easier. Whoa, that was fun. I don't know what just happened there. There it is. Maybe we just have 2. If that happens, we have to acknowledge where the rest of the energy went. Where did it go? It went to other forms, right? So So I want you to get used to this, and you may want to draw this picture either below the one you have or maybe just adjust yours, whatever makes you happy. If the system is the mass, do you remember this? We did this a while ago. If the system is the mass, we're losing some energy to the surroundings, okay? And you can just say that. Okay? What would happen here? Would this one look like this now? Yeah?
No, it wouldn't look like that. It'd have less.
It would have less. How much would it have, kind of given our pattern here? How many bars of spring potential energy would it have?
2. Well, did you cut out 2? Okay, then we 1, yeah.
What decision did you make? 1? So it's going to be like this? And what am I going to have to do in between there? It's going to go to the surroundings as well. Does that make sense? This is called damped harmonic motion. If work is done on the mass, so we are taking energy away, the amplitude is going to go down, okay? Energy is going to be lost, amplitude is going to be lost, and eventually we're not going to have any oscillation. Does that make sense? What if, instead of losing energy, we put energy into the system? Can you imagine that? Have a good week, Emily.
You too.
Can you imagine a situation where I put energy into the system? What does that do? What does that do to the amplitude? It goes up, right?
Yeah.
I am going to wager that you have all experienced this. Not with springs, but what was one of the other examples of simple harmonic motion that we talked about? Swings, right? You've never been on a swing? Okay. You need to find a friend. You guys need to go to the park this weekend, okay? When you were a little kid, you probably sat on a swing and you probably got moving, right? And if you just are left to your own devices and you don't know what to do, you're just going to sit there, you don't know what's going on. But if you have a friend, that friend, if you ask really nicely, might give you a little, what? A little push. That would be applying a force over a,
Distance.
well, distance and time. I guess it's both true. I was thinking distance in this case because a force over a distance is doing some work. So that's going to add some what to your system? Energy. And so then instead of losing energy each time, it's going to be gaining energy each time. And if it's gaining energy in terms of that potential energy, your amplitude is going to go higher and higher. Does that make sense? So if you do the opposite, we have what we call driven harmonic motion. In driven harmonic motion, the amplitude will increase. Not always. It has to be done in a careful way. We're going to talk about that in just a second. Damped harmonic motion, the amplitude is going to go down. Okay? We're going to spend a little bit of time here. We've got about, 13 minutes left, and we're going to talk for those 13 minutes or so about this driven harmonic motion. I wanted to introduce you to a website called, it's videos called The Mechanical Universe. I don't know if you've ever seen these or heard of these. These were made probably quite a few years ago. They're a little bit lame, but sometimes they're really good. And if you need to see another example of something, this would not be a bad place to look. Every time I look for it, I just Google Mechanical Universe, and it comes up. It's the first thing to come up, okay? And there are videos about pretty much, you can't see it because it's not super big, but everything. It's all in here. So, it might just be a place to take a glance if you are looking for something to get a little help. Oh no, for real? Oh, Hold on, we're gonna see if we can get this. Otherwise, it was working before. There we go. I'm gonna show you a little bit of this because I think it's kind of nice. Taylor, can I have you flip the lights off for me? This guy's really old school. We're not gonna watch him. I really want this to work.
1st of July,
There we go. Some of you may have seen this in accelerated physics, I'm not sure.
delegation of citizens met in Washington State. The weather was beautiful, the occasion historic, and the speech-making and fanfare altogether appropriate. This was the grand opening of the Tacoma Narrows Bridge. From the beginning, the bridge, which spanned Puget Sound between Seattle and Tacoma, was traveled in style, as well it should have been.
How many of you guys have seen
The Tacoma Narrows Bridge was one of the longer suspension bridges on Earth. And if somebody hadn't overlooked something, it probably would have remained one of the longer suspension bridges on Earth. The problem wasn't that right from the beginning, a lot of people didn't pay a lot of attention to details. They did. But somewhere along the line, and this was obvious in the end, it looks as if someone forgot the significance of resonance.
Resonance is driven harmonic motion done right, or wrong in this case.
Did you see that part of this?
Resonance. Just as its sound lingers in the air, the word itself remains in the language. Resonance, from a Latin noun meaning an echo. But resonance conjures up more than linguistic echoes. In battle, for example, one hears of the resounding victory. But setting connotations aside, resonance can be seen as a simple mechanical principle of the physical world. Pleasant sounds are usually pleasant precisely because of the way they resonate. Of course, artistry is a factor, so are composition, setting, and mood. But resonance is essential. With a violin or a cello, the strings' vibrations at hundreds to thousands of cycles per second cause the whole instrument to vibrate at the same frequency. Every vibration gives the instrument sound box a tiny push, so that the sound box vibrates resonantly. In turn, those vibrations excite resonant vibrations of the air inside the sound box. The quality of a fine instrument lies precisely in its ability to resonate equally with every note that's played.
No. Come on. There we go.
When a vibrating system is pushed or driven at the natural frequency of that system, resonance occurs. Inside a piano, vibrating strings make the soundboard resonate. This resonance is being driven by the natural frequency of the string, which is about 256 pushes per second at middle C. Each time the string is struck, it makes thousands of oscillations, each one adding to the resonant response of the soundboard. Repeatedly pushing an oscillating system with even a small force each time makes successive oscillations grow bigger and bigger.
Okay, that is the key right there. So I'm going to play that one more time. You might want to write that down. That's a really important statement. But before I do, I want to make sure that it really makes sense to you, okay? We're going to start looking at sound and music after I get back, because sound and music, it's really just simple harmonic motion. You guys seen one of these before? It's a tuning fork, okay? A tuning fork gets us into sound, it gets us into waves, but really here's the secret. A tuning fork oscillating is exactly the same as a mass on a spring. It's just that the tuning fork has a really, really high K value, okay? So when I strike this, it vibrates back and forth and back and forth and back and forth 256 times every second, and that's what causes that sound to happen, okay? So that's one little piece that I wanted to make sure makes sense to you, and then I want to see if we can get this to play one more time so that you can catch that definition.
Makes successive oscillations grow bigger and bigger. The results are vibrations of increased amplitude. Even if these pushes are quite small, resonance will result.
Okay, did that make sense to you all? So little pushes at the same frequency as the thing is oscillating will cause the amplitude to get bigger. That's why when you're pushing somebody on a swing, right, it's not that you just like randomly push them, okay, that's not going to make their amplitude get bigger. You push them once a cycle, right? You push them once a cycle, and if you push them once a cycle, their amplitude will get bigger, okay? When you get to be a big kid and you start using your own legs to pump, right? If you've ever watched a little kid who doesn't actually know how to do it yet, and they just want to be like the big kids, they're sitting on the swing and they go like this. And it's really funny and everybody laughs at them because, well, all the big kids laugh at them because the big kids know that you want to stick your legs out once a cycle, right? And then pull them in once a cycle. And that is what's going to cause that extra force. Okay? That's what resonance is. Resonance is that driven motion, but it has to be done right.
Vibrating tuning fork sets the surrounding air molecules into harmonic motion. Because air works as an elastic medium, it's a good conductor of traveling oscillations or waves. Each oscillation gently and rhythmically pushes against the air, sending out waves at the natural frequency of the tuning fork. When the pitch of the note struck on the piano is the same as that of the tuning fork, even if the fork isn't actually struck, waves from the piano can disturb it and set it into motion by means of resonance. The tuning fork and the piano string are examples of naturally oscillating systems. And though they appear more complicated, they obey the same basic differential equation as the simple mass on a spring.
And we're not going to get scared by the fact that he said differential equation. We're just going to say equation. By the same equation, that's all you need to know. This is pretty cool. I want you to watch this without freaking out. Oh, wait, we know that, don't we?
Yeah.
Look at that. That's just Hooke's law. Whoa, no big surprise, right? Okay? And this thing here, that cosine curve, we're not surprised by that either. That's what you're going to do on Tuesday in your lab. Okay, so let's pay attention because that's important stuff. Whoa, and that X and the F are always going in opposite directions. Who knew? You did.
Like a mass on a spring,
Yeah.
they have an internal force, F, that naturally opposes any disturbance, X.
Oh, you know what that means, right? We're not going to freak out about that. Like,
means
whatever, that's
a
A.
differential equation
Psh, that's just A. Psh, no big deal.
whose solution is a sine
Oh,
function
you've seen that before.
representing oscillations at a natural frequency, omega naught.
This is what we did at the beginning of class
Depends on
today.
the characteristics of the system.
I just didn't have it animated. So here's the animation. Whoa, there's the really ugly thing that y'all freaked out about saying, oh no, Miss Cobbling, don't do it. Oh wait, it all goes away.
The mass of the body.
There's the pretty thing. That's the equation that Cora likes. But then we can put it as the 2 pi, right? It's all the
This
same
is
thing.
another oscillating system with a natural frequency. In fact, the child and the swing are a kind of pendulum. The frequency may be 1,000 times lower than the frequency of audible sound, but the principle's the same. A slightly larger mass, this one with longer legs, has learned to provide her own periodic push by shifting her body weight, kicking forward as far as possible, and tucking her legs under.
She's not very good at the tucking part, it looks like.
It's hard.
Not that we're judging.
Correctly applied at the same point on each cycle, that is, in phase, this young swinger displays her mastery of the phenomenon of resonance.
How do you watch her fall off backwards?
She's mastered it, right? Like she's doing really
But a
well.
true mastery of the phenomenon is best achieved by starting with an oscillating force that doesn't produce resonance.
Okay. Now the creepy lady's gonna come on, so I'm gonna turn that off. I just want to make sure that